Yes, sir. Good morning, everyone, and welcome to the online education for the English medium organized by the Education Department of Municipal Corporation of Greater Mumbai. So, today we are going to study the subject science for class 9th, and we are going to continue with the topic of study of sound. So, this is the second session in the series of revision of the chapter, and today we are going to study in detail about the concept of reflection of sound. Okay, so before we move in, let us first of all revise the topics that we are learning in this chapter. So in this chapter, we are going to learn about sound waves, then about velocity of sound, reflection of sound, the human ear, audible sound, infrasonic sound, and ultrasound. Okay, so let us first of all revise whatever things that we have done in the previous class. So in the previous class, we have seen concepts relating to definition of sound, then properties of sound waves, then longitudinal waves, transverse waves, characteristics of sound waves. Then we have studied about velocity of sound and variation in velocity of sound. Let us study about this in quite detail now. So we had seen the definition of sound. So sound is defined as a sound is a form of energy which creates a sensation of hearing in our ears. So there are various kinds of sound energies, and there are various kinds of energies, out of which sound is one form of energy, right? So it is a form of energy which travels through a medium, right, and creates a sensation of hearing in our ears. Then let us study about the properties of sound waves. Sound energy travels in the form of waves, and a medium is necessary for the propagation of the sound waves. So if you look at the diagram below, or the animation there, you can see that there is a speaker on the left hand side. So when the speaker produces the sound waves travel through the air in the form of vibrations of the air molecules, and as a result, the sound waves travel from the left hand side to the right hand side. Okay, so a speaker has nothing but a small vibrating surface, right? So whenever any object happens to vibrate or oscillate, means whenever it moves back and forth, it generates a vibration or an oscillation, which generates a sound wave, right? And which will travel through the medium. Then next, sound waves gives rise to a chain of compressions and rarefactions in the medium. So compressions are regions of high pressure, whereas rarefactions are regions of low pressure. So if you can observe one of the particles there, you can see the particle is just moving from left to right on its mean position, right? But as a result, what happens is the sound energy gets transferred from one particle to another particle. So as you can see, there are a series of compressions which are regions of high pressure, and series of rarefactions which are regions of low pressure. So you can see those alternate regions of compressions and rarefactions which make up the sound wave. Okay, then let us now study about the types of waves that we have. There are two types of waves basically. The first is a longitudinal wave and the other is the transverse wave, right? So in a longitudinal wave, the particles of the medium oscillate about their mean positions in a direction parallel to the propagation of the wave. Now in this case, you can see the particles are vibrating from left to right, right? So that means what? The particles are oscillating about their mean positions from left to right. But if you look at the direction of the wave happens to move from left hand side to the right hand side of the screen, right? So in this case, you can see the direction of vibration, that is the direction of oscillation, and the direction of motion of the wave, they both are parallel to each other, right? So such kind of wave is called as a longitudinal wave. Let us see the next step, which is a transverse wave. In a transverse wave, the particles of the medium oscillate about their mean positions in a direction perpendicular to the propagation of the wave. So in this case, if you look at any of those particles which are highlighted by the red color, you can see the particles are moving up and down, right? But the overall direction of the wave is from left to right. Okay, so in this case, the direction of oscillation of the particle, which is up and down, and the direction of motion of the wave, which is from left to right, they both are perpendicular to each other, right? So such a wave is called as a transverse wave, right? So a sound wave can be shown in the form of a graph. At any moment during the propagation of sound wave, we can find alternate bands of compressions and rarefactions of the medium, that is bands of high and low density. Okay, so if you look at the diagram here, you can see that there is a loudspeaker on the left hand side. Okay, so as the loudspeaker vibrates, what happens? It creates compressions and rarefactions of the medium, right, which move away from the speaker. Okay, so these compressions and rarefactions can also be shown in the form of bands of vertical lines, Wherever there are compressions, you can see those bands, they are placed very close to each other. Whereas wherever you see there are rarefactions, you can see those bands have moved away from each other, right? These bands can be shown in the form of wave, where wherever you have the high pressure regions, you can see there is a crest, that is the top part of the wave. Wherever there are rarefactions, you can see the bottom part of the depression of the wave, right? So this can be shown in the form of a wave. The next is what we are going to see, the different characteristics of a sound wave. The first one is what? The wavelength. The distance between two consecutive compressions or rarefactions is called as a wavelength. It is indicated by the Greek letter lambda. As you can see in the diagram, it is the distance between two successive compressions or rarefactions, right? Then the next one is what? The frequency. The number of oscillations per unit time is the frequency of a wave. It is indicated by the letter or symbol nu. Okay. So as you can see here, on the left hand side, we have the wave having a longer wavelength, right? That means it has a lower frequency. Whereas on the right hand side, you have the wave of a shorter wavelength, which is having a higher frequency. So both of the waves happen to move with the same velocity to the medium. The next one is what? Amplitude. The amplitude is the maximum value of pressure or density. It is indicated by the letter A. So amplitude is how loud or soft a sound is. So a wave having a higher amplitude will be louder, whereas a wave having a smaller amplitude will be softer. Next is the time period. The time taken for one complete oscillation of pressure or density at a point in the medium is called as a time period. It is indicated by the letter T. So if you look at the diagram here, one complete wave comprises of a crest and a trough, right? So as you can see in this diagram, the region between the two dotted lines is one complete wave, right? So a crest represents a compression and a trough, which is a depression, indicates a rarefaction. So a time required for that one complete wave to pass through is called as what? The time period. Next is the pitch. The value of frequency determines the pitch of the sound. Low pitch sound is of low frequency, whereas high pitch sound is of high frequency, right? So the low pitch sound is a sound generated generally by males or men. Men, when they talk, they have a frequency which is generally lower. Whereas when women or girls, when they speak, they have a shrill sound, right? So women speak with a high frequency sound, so we call it as a high pitch sound. Okay. So next concept is what about the velocity of sound. So distance covered by the point on the wave in a unit time is the velocity of the sound wave, and velocity equals to distance upon time. Any point on the sound wave covers a distance equal to lambda, which is the wavelength in time period t. Thus, the velocity is given by v equals to nu into lambda. We know that 1 upon t, which is time period, t is equal to nu, which is frequency. Hence, we can write velocity equals to wavelength upon time period, that is v equals to lambda upon t. Okay, so velocity of sound equals to wavelength into frequency. So in any medium at fixed physical conditions, the velocity of sound of different frequencies is very nearly the same. The velocity of sound is highest in solids and least in the gases. It increases with an increase in temperature of the medium. Okay, let us see about, or let us discuss about the variation of the velocity of sound. First is what? Variation with temperature. The velocity of sound is directly proportional to the square root of the temperature of the medium. That means the velocity of sound V is directly proportional to square root of the temperature. This means that increasing the temperature 4 times doubles the velocity. The next is what? Variation with density, that is rho. The velocity of sound is inversely proportional to the square root of the density of the medium. That is, V is inversely proportional to square root of density. This means that increasing the density 4 times reduces the velocity to half of its value. Then next is what? Velocity, variation of velocity with molecular weight. The velocity of sound is inversely proportional to square root of the molecular weight of the gas. This means that increasing the molecular weight 4 times reduces the velocity to half of its value, right? Now this was the content that we had studied in the previous class. Now let us move into the new concept that we will be discussing today. The first one is what? About the types of sounds. So there are 3 basic types of sounds: audible sound, infrasound, and ultrasound. Now, these type of sounds are classified based on the ability of humans to hear these sounds. Okay, so you can see audible sound has a frequency range from 20 hertz to 20,000 hertz. Now, what is this hertz? 1 hertz is 1 vibration per second. Means whenever an object vibrates or oscillates once every second, it is said to be 1 hertz. So when you see that a frequency of 20 hertz means any object vibrating 20 times in 1 second. Okay, so audible sounds are frequencies from 20 hertz to 20,000 hertz. Next is what? Infrasound. Infrasounds are frequencies lower than 20 hertz, and ultrasounds are frequencies higher than 20,000 hertz. Okay, then next one. Let us now discuss in detail about the types of these sounds. The first one is what? Your audible sound. The limits of hearing of the human ear are 20 hertz to 20,000 hertz. The limits of human ear are 20 hertz to 20,000 hertz. The human ear can hear sound frequencies in this range. These sounds are called as audible sounds. Human ears cannot hear frequencies lower than 20 hertz and higher than 20,000 hertz. That means us humans, we can only perceive sounds which are having a frequency range of 20 hertz to 20,000 hertz. Means any object which vibrates 20 times per second to up to 20,000 times per second. Such sounds we can hear. So if you have an object is vibrating less than 20 times in a second, those sounds we cannot hear. Right? Same way, if any object happens to vibrate more than 20,000 times per second, these sounds also we cannot hear. Okay. Next one is what? Your infrasound. Sound waves with frequencies smaller than 20 hertz are called infrasounds. The sound produced by a pendulum and the sounds generated by the vibration of the Earth's crust just before an earthquake are examples of infrasound. Right? So you might have seen a pendulum in a wall clock. So that pendulum moves left to right very slowly. But even if it is moving slowly, it is vibrating, it is oscillating. Right? So it is producing some sound. But our human ears, they are not able to listen to that sound frequency. And such sounds are called as infrasounds, having frequency less than 20 hertz. Okay. Then next is what? Your ultrasound. Sound waves with frequency greater than 20,000 hertz or 20 kilohertz are called ultrasound. Right? 20 kilohertz means 20,000 hertz. 1 kilohertz is 1,000 hertz. Okay. Now, dogs, mouse, bats, dolphins, etc. have a special ability to hear ultrasonic sounds. They can sense some noise which are inaudible to us humans. Means these animals, dogs, mouse, bats, dolphins, etc., their ears can perceive, can listen to sounds which are greater than 20,000 hertz. Children under the 5 years of age and some creatures and insects can hear frequencies up to 25,000 hertz. That is 25 kilohertz, right? Then next, bats, mice, dolphins, etc. can also produce ultrasound. Means along with the ability to hear ultrasounds, they can also generate ultrasounds. Then, the ultrasounds are used for communication between ships at sea. So if you have two ships at sea, right now in the sea, there won't be any communication lines. There are not going to be any telephone lines. You cannot have mobile phone towers at sea, right? So there won't be any communication methods at sea. So two ships at far away distances, they can use ultrasonic sound waves to communicate with each other. Okay, so there are specific devices, specific radio devices used which can transmit and capture ultrasonic sound waves. Then ultrasonics are used to obtain images of internal organs in a human body. Now these concepts we are going to learn in the further classes. Okay, then ultrasound is used to locate cracks and faults in the metal blocks. So if you have any piece of metal, right, and if you want to detect the presence of any cracks which may be present in the internal surface of the metal, which will not be visible from the top, for finding out such cracks, we can use ultrasonic machines, ultrasound machines, right? Now, such machines are used by railway authorities. They are also used by Indian Railways, right? So, these railway, they have technicians who will keep on checking the tracks for formation of any cracks. Okay, so if they happen to have any crack, what will happen? They will just cut out the piece and replace the track with a new piece. Okay. Next is the concept relating to reflection of sound. Okay. Now, like light waves, sound waves too get reflected from a solid surface or a liquid surface. Sound waves also follow the laws of reflection. We are aware about the laws of reflection, right? A smooth or a rough surface is needed for the reflection of sound. The direction of incident sound wave and the reflected sound wave make equal angles with the perpendicular surface, and all these three lie in the same plane. Now, if you look at this diagram here, we have a hard plywood surface which acts as a reflecting surface. Okay. Now, placed perpendicular to the hard plywood is a piece of softwood, right? Then, on the left hand side of softwood, we have a stopwatch which is kept, and there is a cylindrical cardboard tube which is placed in front of the stopwatch, which makes a certain angle with the softwood and the hard plywood, which is I, which is the angle of incidence. Okay. When sound travels from the stopwatch through the cardboard tube, it gets reflected from the hard plywood, obeying all the laws of reflection. Means angle of incidence equals to angle of reflection. So the reflected sound wave now travels on to the other side, where one more cardboard tube is kept so that the sound waves can be channeled, and the sound waves can be passed on to the other side where the listener can listen, right? So even though there is a barrier in between, which is a wall of softwood, the person on the other side of the wall can listen to the sound of the ticking stopwatch. This proves that sound waves do get reflected from the hard plywood surface. Okay. Now let us move on further. Now we will now talk about the good and bad reflectors of sound. Now, depending upon the type of the surface from which the sound is getting reflected, the reflecting surfaces are classified as either good or bad reflectors of sound. Let us see. How much of the incident sound gets reflected decides whether a reflector is a good or a bad reflector. So, if maximum amount of sound waves get reflected from a surface, then that surface is said to be a good reflecting surface, right? If the sound waves are not able to get reflected from a given surface properly, then that surface is said to be a bad reflector of the sound. Okay. A hard and a flat surface is a good reflector, while clothes, paper, curtains, carpet, furniture, etc. absorb the sound waves instead of reflecting it. Hence, they are called as bad reflectors. Right? So you can see in this diagram, the incident sound gets reflected from the surface. The sound may get absorbed, it may generate some amount of heat, it may also be transmitted on the other side of the wall, right? So the transmitted sound as well as the absorbed sound, they cause what? The decrease in the amount of reflected sound, right? Then next important characteristic of sound is relating to an echo. Now, echo is a very interesting phenomena which you might have observed, right? Let us see it in detail. Now, you must have visited an echo point at a hill station. If you shout out loudly at such a point, you hear the same sound just after a little while. This is called as an echo. Now, exactly how does an echo form? That is what we are going to study now. Okay. So, an echo is a repetition of the original sound because of reflection from some surface. So, if you have visited at a hill station somewhere, something like Mahabaleshwar or maybe Mount Abu or some other hill station. Now, at this location, you generally happen to have a echo point. Now, what happens if you go and stand at that echo point, and if you shout, you will get to hear your same sound repeated after a certain time interval, right? Now, for this to happen, there must be a large reflecting surface somewhere. So generally on a mountain top, when you look across, there might be some another mountain, right? So when you shout, what happens? The sound waves coming from your mouth, they travel in all directions, right? They go in front of you and happen to strike the mountain in front of you. Once the sound strikes that mountain, then it gets reflected and comes back to you, which you happen to hear as a reflected sound. Okay, so let us see. What are the conditions? Now let us see what are the conditions which are required for us to hear a echo. Okay. So in order to be able to hear the original sound and its reflection distinctly at 22 degrees Celsius, what must be the minimum distance between the source and the reflecting surface? As we had discussed, on the mountain top, when you are shouting, there might be a mountain in front of you, right? So for us to hear the echo, how far should be the other mountain be from you, right? That is what we will be discussing. Now, at 22 degrees Celsius, the velocity of sound in air is 344 meters per second. Okay. Now, our brain retains this sound for 0.1 seconds. Now, what does this mean? Whenever any sound reaches into our ears, it is registered in our brain. Means it is perceived by our brain as sound. Right. Now, when a particular sound frequency reaches into our ears, right, our ears lose the ability to listen to that same sound for a time interval of 0.1 seconds. Right. That means you cannot hear the same sound for a time interval of 0.1 seconds. You can hear it after 0.1 seconds. Okay. This is called as persistence of hearing. Okay. Let us look into it. Now, our brain retains this sound for 0.1 seconds. Thus, for us to be able to hear a distinct echo, the sound should take, means the reflected sound should take more than 0.1 seconds after starting from the source to get reflected and come back to us. Now look at that diagram here. Look at that animation. There is a person who is shouting or generating a sound. Now that sound travels up to that object, which is the reflecting surface. In this case, it is a wall, right? It gets reflected and it comes back to you. So the distance traveled by the sound is double the distance from the object to the person, right? And the minimum time interval that the sound wave should take should be greater than 0.1 seconds. Okay. Now we can determine the minimum distance between the source and the reflecting surface as follows. Now we know the formula for speed. Speed equals to distance upon time. If we rearrange the formula, we get what? Distance equal to speed multiplied by time. On substituting the values, the value for the speed of sound is 344 meters per second. And the minimum time interval after which the sound should reach back to you is 0.1 seconds. Right? So the distance comes down to 34.4 meters. That means the sound has to travel a total distance of 34.4 meters. Remember, it is a total distance. Total distance means from the source of the sound, that means from the person up to the distance, up to the object or the reflecting surface, and then back again. That total distance should be 34.4 meters. That means what? The actual distance should be half of it. Thus, to be able to hear a distinct echo, the reflecting surface should be at a minimum distance of half of the above, that is 17.2 meters. That means the sound will travel 17.2 meters from the source, that means from the shouting person, up to the wall, that is the first 17.2 meters. And then once it gets reflected, it will come back the return 17.2 meters. So total distance will be 34.4 meters, and that will be happening in a time interval of 0.1 seconds. So if you want to hear that echo, our brain will register that same sound only after an interval of 0.1 seconds, right? So that should be the minimum distance. Any distance greater than 17.2 meters, then the time interval between the original sound and the echo will go on increasing. But if the reflecting surface is at a distance smaller than 17.2 meters, then the person will not be able to hear the echo. Okay, very nice. Now, the next concept is relating to a phenomena relating to the reflection of sound, which is called as reverberation. But it is one of the undesirable properties. We do not want a reverberation to occur. Reverberation is not a good property. Okay, we will discuss why. Let us compare the two cases. First one, go to an empty closed house with your friends. Once inside, chat with your friends and note what happens. Okay. In the second case, close the doors and windows of your house and switch on the music system. Increase the loudness of the system as much as possible, and again note what do you observe. Okay, let us discuss what happens. In the first case, the echoes of the sounds of the friends are heard. After some time, it will become difficult to hear one another. Okay, so when you are present with your friends in a closed room, what will happen? The walls of the closed room will reflect the sound waves in different directions, and more multiple reflections of the sound waves will create disturbance. due to which you will not be able to hear what everyone is speaking. Okay. For the second case, the sound of the music seems like jumbled and prolonged. It becomes highly undesirable to listen to this sound after some time due to multiple reflections of the sound. Okay, let us see what happens. Sound waves get reflected from the walls and roof of a room multiple times. Repeated reflections of sound waves from the walls combine to build up what seems like a continuous sound. This causes a single sound to be heard not once but continuously. This is called as reverberation. Now look at the diagram. Okay. Now in this case, you have a large auditorium, okay, or a room. Now in this case, on the left hand side, you can see there is a speaker. There is a person who is speaking or maybe singing or maybe talking, who is standing on the stage, and there is a listener who is sitting on a chair on the right hand side. Now, when the person is singing or speaking or creating any kind of a sound, the sound first of all travels directly to the listener in a straight line. But whenever sound is generated, sound travels in all possible directions from the source of the sound. So sound will also get traveling to the walls as well as the ceiling of the room. So from there they will get reflected. Right. Now if you look at those other sound waves, they happen to travel different distances when it is reaching the observer or the listener. So in this case, what will happen? As the sound waves are traveling different distances, they will take different amount of time to reach the listener, which will create what? A continuous sound. Okay. Let us see. The time between successive reflections of particular sound wave reaching us becomes smaller, and the reflecting sound gets mixed up to produce a continuous sound of increasing loudness which cannot be heard clearly. Now look at this diagram again. It is a similar one to the previous diagram, right? You can see on the stage there is a person speaking, right? So first of all, the direct sound reaches to the listener in the shortest possible distance in a straight line. But as we know, sound also travels in all possible directions. So you can see the reflected sounds, multiple paths. It takes place different directions, different paths, right? It can also get reflected from any feature on the wall or the ceiling of the room, right? And in that case, the sound waves happen to travel more different distances. So the sound will take different amount of time to reach to the listener, right? Which creates what? A continuous sound of increasing loudness, right? Excessive reverberation is not desirable, as the speech of the speaker or the pitch of the music cannot be heard clearly due to the mixing of reflected waves and direct waves produced after the production of the earlier waves. That means all the different waves, the direct waves as well as the reflected waves, they all will get mixed up and get jumbled up. So the listener will not be able to listen to what the speaker is saying. Okay. Now, some auditoriums, public halls, or buildings are considered to be acoustically poor because of reverberation. The word acoustics means relating to sound energy. Okay. So, to reduce reverberation, the roof and walls of auditoriums are generally covered with sound absorbing materials such as compressed fiber boards, rough plaster, or curtains. Even the materials of the seats is chosen such that it absorbs sound waves to a desired extent. So, if you have ever visited a movie theater or an auditorium, right? And if you have observed the walls and ceilings of the auditorium or the movie hall carefully, you must see those surfaces are soft materials, or there might be holes, or there might be different designs or different shapes which are built into the walls. They are there to reflect the sound in different directions and avoid the formation of reverberation. Okay, so let us see certain questions that I will expect students to be continuing, right, or preparing. So first of all, define audible sounds, infrasounds, ultrasound, echo, and reverberation, right? So you need to just define, you can just find those answers in the textbook. Second question, what must be the minimum distance between the source and the reflecting surface at 22 degrees to provide an echo? Right, so that discussion we had seen how to calculate the distance of 17.2 meters, right? And then state the various methods to reduce the reverberation. Okay, so that is the content for today, right? Let us, before we conclude the class, let us just revise whatever things that we have done today. Okay, so Today's class, we have started with the different types of sound. So there are three types of sound, namely audible sound, infrasound, and ultrasound. These three types of sounds are categorized based on the ability of humans to hear the sounds. Okay. So audible sounds have a frequency from 20 hertz to 20,000 hertz. That means the sound produced by objects vibrating 20 times per second to up to 20,000 times per second. Okay. The next is what infrasound, frequency lower than 20 hertz, and ultrasound is frequency higher than 20,000 hertz. Okay. The next, audible sound. The limits of hearing of the human ear are 20 hertz to 20,000 hertz. The human ear can hear sound frequencies in this range. These sounds are called as audible sounds. Human ears cannot hear frequencies lower than 20 hertz and higher than 20,000 hertz. Okay. Next is what? Infrasound. Sound waves with frequency smaller than 20 hertz are called infrasounds. The sounds produced by a pendulum of a clock and the sounds generated by the vibration of the earth's crust just before an earthquake are examples of infrasound. Right. So these sounds produced by earthquakes, which are in the which are in the infrasound region, they can be heard by some animals and birds. That is why it is observed by scientists that just before an earthquake, several animals happen to get alerted and they happen to get uh, they happen to start running in different directions, right? Just because they happen to sense these infrasonic sound waves just before a earthquake. Next is ultrasound. Sound waves with frequency greater than 20,000 hertz are called as ultrasound. Dogs, mouse, bats, dolphins, etc. have a special ability to hear ultrasonic sounds. They can sense some noise which are inaudible to us humans. Inaudible means we cannot hear those sounds. Children under 5 years of age and some creatures and insects can hear frequencies up to 25,000 hertz, that is 25 kilohertz. Bats, mice, dolphins, etc. can produce ultrasound. Now, if you look at this diagram below, what do we have? We have a bat which is flying, and there is a prey of the bat, might be some small insect or a butterfly. When the bat is flying in the darkness, it continuously generates what? The ultrasonic sound waves. These ultrasonic sound waves happen to strike on the obstacles, on the walls, on the trees, or any other obstacle in between and get reflected. Now, these reflected sound waves are now received or heard by the bat, and the bat can create a mental picture of whatever things are present in front of him. Right. So, by observing the reflected sound waves, the bat can determine the exact position of the insect, and then he can just go in that direction and eat that insect. Okay. Then, ultrasound is also used for communication between ships at sea. It is used to obtain images of internal organs in a human body. The device is called as a sonography machine, right, which we will be studying in the next class. Then ultrasound is also used to locate cracks and faults in metal blocks. Okay. Then next is reflection of sound. Like light waves, sound waves too get reflected from a solid surface or a liquid surface. Sound waves also follow the laws of reflection. A smooth or a rough surface is needed for the reflection of sound. The direction of incident sound wave and the reflectant sound wave make equal angles with the perpendicular to the surface, and all these three lie in the same plane. So we had just discussed as you can see the diagram here, where we have a source of sound which is a stopwatch, which is placed in front of a hard plywood. There is a partition of soft wood placed, and on the other side there is a listener. So the sound waves from the stopwatch will travel up to the hard plywood and get reflected. In this case, the angle of incidence made by the sound wave will be equal to the angle of reflection. Thus, it obeys the laws of reflection, right? So we have good and bad reflectors of sound. How much of the incident sound gets reflected decides whether a reflector is a good or a bad reflector. A hard and a flat surface is a good reflector, while clothes, paper, curtain, carpet, furniture, trees, then leaves and plants, right? They happen to absorb sound waves instead of reflecting it. Hence, they are bad reflectors. So, if you happen to observe this wall here, the incident sound gets reflected. So, some of it gets reflected, but some of the sound is absorbed and some of it is transmitted. right? So the amount of sound reflected is less than the amount of sound that is incident. But in this case, it happens to be a bad reflector of sound. Okay. Next concept we studied today was about an echo, right? So you must have visited an echo point at a hill station. If you shout out loudly at such a point, you hear the same sound just after a little while. This sound is called as an echo. So an echo is a repetition of the original sound because of reflection from some surface. Okay. Now let us see the conditions that are required for us to able to be hear an echo. Okay. So in order to be able to hear the original sound and its reflection distinctly at 22 degrees Celsius, what must be the minimum distance between the source and the reflecting surface? Let us see. At 22 degrees Celsius, the velocity of sound in air is 344 meters per second. Our brain retains this sound for 0.1 seconds, as I told you, right? Thus, for us to be able to hear a distinct echo, the sound should take more than 0.1 seconds after starting from the source to get reflected and come back to us. Okay, we can determine this distance as follows. We know the formula for speed equals to distance upon time. So we can say distance is equal to speed into time. So we can see speed of sound is 344 meters per second and the minimum time interval is 0.1. So you get the distance as 34.4 meters. But this is the total distance, that is from the source to the reflecting surface and then back again to the source, who is the listener now. Okay. So thus to be able to hear a distinct echo, the reflecting surface should be at a minimum distance of half of the above, that is 17.2 meters. Right. Next we study the concept of reverberation. Right. Let us see what is reverberation. Sound waves get reflected from the walls and roof of a room multiple times. Repeated reflections of sound waves from the walls combine to build up what seems like a continuous sound. This causes a single sound to be heard not once but continuously. This is called as reverberation. Okay, the time between successive reflections of a particular sound wave reaching us become smaller and the reflected sound get mixed up to produce a continuous sound of increasing loudness which cannot be heard clearly. As you can see, we had discussed, we have the source of the sound on the stage and a listener. So when the source of the sound creates a sound, the sound waves travel in all directions from the source of the sound. So the first sound reaches in the form of direct sound in a straight line to the listener, right? The other waves travel in all direction above and in front of the source of the sound, right? So they can get reflected from the different paths, the multiple paths that the sound wave will take, right? As you can see, the sound waves take different paths and all of those different paths have different distances up to the listener, right? As they are traveling more and more and different distances, the sound will take different amounts of time to reach to the listener. Hence, after the original sound, the reflected sound will start reaching and the listener will get a continuous sound of increasing loudness, because of which what will happen, the listener will not be able to hear what the speaker is exactly saying, right? Excessive reverberation is not desirable as the speech of the speaker or the pitch of the music cannot be heard clearly due to the mixing of the reflected waves and direct waves produced after the production of earlier waves. So how to reduce reverberation? Let us see. Some auditoriums, public halls and buildings are considered acoustically poor because of reverberation. To reduce reverberation, the roof and walls of auditoriums are generally covered with sound absorbing materials such as compressed fiber boards, rough plaster, or curtains. Even the materials of the seats are chosen in such a way so that it absorbs the sound waves to the desired extent. Right? So this is how the reverberation can be reduced. So this is how we complete the class for today. Right? So if students happen to have any questions, you can please raise your hands and ask the question. Yes, students, please go on. Yes, students, please, if you have any doubts, you can raise your hands and ask the question. Yes, madam. Hello. Hello, madam.
Yes, sir.
Yes, madam. So I have concluded the class. I don't think so anyone has any doubts. So we can end the class for today.
Okay.